Hello, I'm James Ingram for AutoControls-dot-org. Welcome to video number 808, which is titled A Demonstration of a DCC-Bitswitch Block Bit Switch. These DCC-Bitswitch units stop DCC trains by suddenly changing the current on the track from DCC to DC current, which causes them to stop. This works on almost all DCC systems that follow the NMRA recommended practice 9.2.4. I'm told it probably won't work on MRC systems because they apparently didn't follow the standards, and it probably won't work on Lionel and MTH systems because they're proprietary systems and apparently don't fully follow the NMRA standards. This video shows a single DCC Bitswitch unit, which is by my hand here, and videos on the DCC-Bitswitch.com website and on the YouTube channels for DCC-Bitswitch and Fred Hughes show more complex operations. Note there's three ways to stop these DCC trains. The way we're using in this video is method number one. We use what DCC-Bitswitch calls a DC break generator, which is this unit right here, which converts DCC to DC, and the bit switch sends it out to the break section when required to stop a train. That's what we're using in this video. The other two ways that we're not using in this video, but just to mention them, is you can also use what DCC-Bitswitch calls a set speed zero generator, which is basically an electronic board, there it is in a protective wrapping, that sends out a set speed zero command, but you need another booster unit to use this unit, so it's a little more complicated and a little more expensive. But this will stop some trains that won't stop using this system. Like I said earlier, if they obey the NMRA recommended practice 9.2.4, this DC signal will work. But on engines that won't obey that, this will usually get them stopped. The third method is what they call asymmetric DCC, which uses diodes to make like an uneven DCC signal. In other words, the positive might be larger than the negative. They cut one side down by using diodes, but this only works for lens and Zemo decoders. These three methods are discussed in more detail by the earlier video, number 803, DCC-Bitswitch Overview, narrated by Fred Hughes. Part 2, at about the 5-minute point, starts discussing all three of these methods. The previous video, 807, titled Demonstrating RP 9.2.4, we showed how we set up these engines to stop on DCC, or to stop on DC, to use with this break signal generator. These colored wires on the bit switch here on its center terminals are yellow for test, red for break, green for release, and black for common. Right now the thing is in the green position, so if I hold one end of this wire across the common terminal, I can put it on the break terminal, which will switch it to red. Now if I hold it across the test terminal, which is a yellow wire, there's no light change, but you may hear the relay switch. Now if I hold it on the green terminal, which is a release terminal, it goes back to green. So basically I'm doing here what the reed switches in the track would do when a magnet with a locomotive passes over them. Again, we'll touch the red brake terminal, then we'll touch the yellow test terminal, and we'll touch the green release terminal, which sets it back to green. This drawing is from the DCC-Bitswitch website under the block Bitswitch part. This is worded probably as well as I can say it, so I'll just read it. It says, when the test contact is triggered, block bit switch simply checks to determine if a leading train has triggered the brake contact, that would be the red light we just threw, but has failed to reach the release contact. If this has occurred, the block bit switch slows the trailing train to a stop using the momentum value stored in CB4. That's the deacceleration variable. Then, reading more, when the leading train has reached the release contact, that would be the green light, and the track contact it sets at the green. When it's reached the release contact, the bit switch will release the trailing train and cause it to accelerate using the momentum value stored in CB3, which is a configuration variable for acceleration. We're back to our drawing from the DCC-Bitswitch website for a simple setup. It refers to this as what's minimum control when you're just using one bit switch. You can have more of them, but this demonstration just uses one bit switch. Here's our DCC command station. Let's go around the loop of track first. Here's the loop of track with the direction of travel clockwise, and the pink part is the brake section. Now over here's the DCC command station, putting DCC current out directly to the main line, and also going to the DC brake generator, which in turn sends both DC and DCC to the bit switch, was shown in here in yellow, and then the bit switch connects to the brake section. And then you've got your brake section. And then you've got your three read switches that signal the bit switch. Your green release relay is over here. Your red brake, not relay, read switch, excuse me. Your green release read switch is over here. Your red brake read switch is over here, usually not far from the exit of the stopping section. And then inside the stop section, shown in yellow here, is the test read switch, is the one which actually does the checking to see if it's green or if it's red. And if it's red, it switches the current from DCC to DC, which will make the engine come to a gradual stop within the stopping section. Several days later, we've got the same bit switch unit now hooked up to this S-gauge track. Where we're looking right now is the far end of the thing. Basically, it's I guess what you call a dog bone, a loop of track that kind of bulges on each end. But we're looking at the far end, and if we come up along the track, there's the bit switch and stuff set up right there. And continuing up to the other end of the loop, where we're going right now with the camera, we'll get up to the front end of the loop. Here's the command station. And going out from the command station right here is the power wires feeding out to the main line, and then off the other end of the command station, or off the other set of terminals from the command station, the same DCC signal is going down down along the edge here and over on this wire, and this feeds the DC brake signal generator, and that goes to the bit switch with four wires, the A and B terminal always carrying DCC, and in the normal automatic mode, this is carrying DC. Remember, when you switch this thing the other way to manual mode, it puts DCC on these wires also, but in a normal operating mode, which is automatic, there's DC going here, and then the bit switch puts either DC or DCC onto the braking section. Anyways, here's the bit switch in going out to the track. This is the track hookup right here for the braking section, and then these are the three read switches connecting here to the bit switch. I've got it tipped up on its side, trying to get the lights to show a little better back where the camera will be sitting. Let's look at the braking section for a minute. It starts back there where that orange piece of cardboard that says insulator on is, and it continues up here to where the other orange piece of cardboard says insulator, and I believe you can see there's the yellow plastic insulating sections that insulate the stopping section from the main line. If we just follow that back again, coming back to the entrance to the brake section again, we have a same pair of the same yellow plastic insulators to insulate the main line over here from the braking section over here. Here's a crude drawing that kind of tries to give you a feel for the currents on each side of the insulating section. Out here is the main line, which is always DCC. Now when the block is green over here, it's going to be the same DCC signal, but if the bit switch is in the red section and a locomotive goes across the test read switch, it'll cause the bit switch to change from DCC to DC in this stopping section, which you'll get a current that looks something like this, some sort of a DC signal that's made by rectifying the DCC signal into DC, and it'll be either positive or negative, but either way, if it was connected with this, it'll cause a short because this is going plus and then minus and plus and minus, whereas this is always going to be either all plus or either all minus, depending on which way it's going. But regardless, you get a short if these rails get connected, so that's why they've got to be insulated to keep these two currents apart from each other. Let's look at these reed switches a little closer. If a train is leaving the stopping section, which is the X of the stopping section is right here by these insulators. If a train is leaving this and it goes over the red track contact, which is right here, that'll set the bit switch to red. And then if a train comes in and goes over the test contact, which is in here, it'll cause that bit switch to actually trigger and change the current from DCC to DC. There, I don't know if you heard the click or not, but I just triggered it with this magnet I got in my hand. There's actually little round magnets here. I triggered it to switch, so it's actually putting DC onto the stopping section now. And then if the other train on the main line goes down here and crosses the release section, probably can't see it, but if it crosses this release section, it'll switch the bit switch back to green, and the train that was stopped in the stopping section will be allowed to start up and exit the stopping section. If we go back to the bit switch drawing again, there's two things to note. Starting with the entrance of the braking section, there's a distance labeled longest train from here over to here, and then there's another distance labeled maximum braking distance from here over to here. So that train has got to be all the way in the block before it goes over the test contact, so there's no metal wheels hanging over the back. And likewise, it's got to stop before it gets up here and bridges this gap, or you'll be shorting the DC in this section with the DCC on the main line. And looking at the actual train here, you can see this train that's parked here is about pretty much the longest train you can have, because the trigger is right here, the test contact is right here, where it's going to switch it from DCC to DC, and then going back here you can see the caboose is just inside the block. Now actually there's a little bit more room because the magnet on this train is on the bottom of the flat car right about here, so that train has to get to about where it's sitting now before the bit switch is triggered to change the current from DCC to DC, and that caboose will be reasonably inside the braking section. Then the other thing, talking about the minimum braking distance, that would be from where the engine is now up to the other end of the block where the other insulating sections are. So basically it's saying this train doesn't want to drift any farther while it's slowing down. It's got to be stopped by the time it gets to here. If it isn't stopped by the time it gets to these insulators, it'll drift over, and again it'll short the DC with the DCC on the main line. I put a cardboard box over top of the bit switch just to try to make the LEDs show a little better without getting washed out by the overhead lights. The bit switch is now green, so a typical scenario is if there was a train in that stop block near the tower there, it would pull out of the stopping section and pass over the brake reed switch, which would set it to red, and then an incoming train would come into the block and go over the test trigger, which would stop that train, and that train would be held in the stop block until the other train on the track went down the main line here and went over the release reed switch, would have set it to green again. I'll pull out one of these reed switches. This is the same type of reed switch, one of the ones we were using for the large scale, and they just it's the same type. It's either a Railroad Concepts or a DCC-Bitswitch reed switch. I'm not sure which, but it's pretty much a generic, semi-generic reed switch, I guess. It just slides under the edge of the track. I usually just slide it till the black part disappears under the roadbed. That seems to work pretty well for the S gauge. I'm going to start this up with one train and run it through. The first time it'll run through the stopping section without stopping because the bit switch is green, as you can see it now. The second time around I'll use the magnet to manually trigger it to red so it'll stop this train. Now it just entered the stop section, but the bit switch is green, so there's still DCC in there and it's not stopping. Now it's about ready to go over the brake contact, and right there it's set the bit switch from green to red. Now the train's behind the camera. In a second it'll go around the other end of the loop and come out down the left track there. Now down at the end of the straight it'll go over the release contact, which will set the bit switch back to green. Now I'm going to manually trigger it back to red. Now that bit switch is set to red, so when that train comes in the stop section and crosses the test track contact, it'll actually change the current in the stop section from DCC to DC, and that engine will slow to a gradual stop. Now that engine's sitting there, there's DC in that stopping section. That engine will sit there and not go anywhere until that bit switch goes back to green. Now if there was a second train on the track, the second train would cross the release contact and release this train. Since there's only one train, I'm going to get down there and manually do it with the magnet, and you'll see that train will start up and exit the block. I've turned the sound on this engine. I'm going to do the same thing, run it into the block, and I'm going to manually use this magnet to trigger set the block to red so it'll stop that engine, and we can observe how it it throttles the sound down and everything, and that engine will sit there and idle while it's stopped. Now the train just set the block back to green, so I'm going to go over here and manually set it to red. Now that block is red, so when that train goes across the test contact, the bit switch will change the current in the stop section from DCC to DC, and that train will stop as before. Now you can see how, and hopefully hear how that engine's sitting there idling still with its lights and things active because it's getting full power, but it's going to wait until the DCC, until the bit switch goes green, and when it switches the track current in that stop section from DC back to DCC, that train will gradually accelerate and leave the stop section. I've added a passenger train to the layout. Now the passenger train is stopped in the braking section. It'll go when the bit switch is set to green by the freight train, which is sitting out there on the main line. That Delaware and Hudson Sharknose engine, it's an American Models running gear with somebody's custom top. It may be American High Rail, I'm not sure. I bought it used at a train show, and then Fred Cup put the decoder and the flashing lights on it for me. Now the freight train's about ready to go over the go contact there. It went to green. You can see the brake section change from DC back to DCC, which allowed that passenger train to start up, and it's exiting. And when it exited the stopping section, it went over the red brake contact, which set the bit switch back to red. So when that freight train that's now entering the stopping section goes over the test lead switch, it'll trigger the bit switch to change the current in that section from DCC to DC, and that engine will come to a stop, which it did. Now that freight train engine will sit there until the passenger train switches the bit switch back to green. There it just went green, so the freight engine will start up and exit. This is all operating under NMRA recommended practice 9.2.4, which dictates that engines that follow that standard when running under DCC and they encounter DC current, which is what's happening here, they'll slow to a stop under their program deacceleration, and that's what these engines are doing. And then when the DCC current is restored to the section, the engines will accelerate under their programmed acceleration. This is basically the same thing we did with the G-scale engine, just doing the same thing in S-gauge. As long as the decoders follow the NMRA standards, it's almost irrelevant what gauge you use, they'll behave the same way. Fred Hughes of DCC-Bitswitch has a video that he runs about, I think, five or so N-gauge trains on a little demonstration layout, and controlled by the same type of bit switches. You can see our freight train is stopped and waiting, and it'll wait until that passenger train reaches the end of the straight section and goes across the green release read switch, which will trip the bit switch back to green. There it goes, and the freight train will take off. I've turned the sound units on these two engines on. We'll do the same two trains, just you can hear what it is with the sound effects in operation. The Tsunami decoders can be programmed so that they automatically give one horn toot when the engine stops, and they automatically give two horn toots when the engine starts up, and these engines have been programmed that way, so the horn toots come automatically. I've taken the diesel passenger train off and put a steam engine passenger train on. That steam engine is a American Flyer K4 Pacific. It's got a DC can motor added by Earl Wagner, and then a DCC decoder added by Fred Cupp. My headlight's not working right now, or the headlight would be staying on when it stopped. the magnet on the steam engine is underneath the tender. Just to comment on attaching the magnets on the steam engine. Some of the engines that have the metal tenders, you can see where my thumb is, the magnets are just stuck on the bottom of the tender, since the bottom of the tender is metal, and that seems to work fine for that engine. On this diesel train, the magnet was glued to the bottom of this flat car. When I say glued, it was actually hot glue is what I mean to say. I earlier in this video used the term rubber cement, and I really should have been saying hot glue. So hot glue is what's attaching that magnet to the bottom of the flat car. And in a similar manner, that Delaware and Hudson shark-nose diesel, this is the first passenger car that was on that train. I was able to hot glue another one of the round magnets on the bottom of this passenger car. Some of the Lionel Flyer freight cars, they have a metal, the truck is metal right here. This part here where my finger is all metal, and you can just stick the magnets to the bottom of the truck. You don't have to glue them or anything. They just stick there because the round magnets attach themselves to the bottom of the truck. So that's another way to handle the magnets. Probably already know this, but this is what a hot glue gun looks like. You plug this, it has a cord on it, you plug this thing in and it heats up, and this is the glue stick sticking out the back here. It's going in here, and when this thing is hot, you pull the trigger and it extrudes hot glue out the nozzle here. So that's one easy way to stick magnets on the bottom of your rolling stock. You can get these things, I think, hobby stores like Michael's and Hobby Lobby, and probably lots of other places also. So far in this video, we've been talking about running in automatic mode. Remember also that the Bitswitch has a manual mode. What is manual mode? Manual mode is basically where you essentially bypass the Bitswitch system, so it has no effect on the track, and you can run your trains entirely in a manual mode as if the Bitswitch system, however many of them you have, as if they were never even there. Let's take a look at this analogy. What I've got set up here is actually in my laundry tub, but if you use your imagination a little bit and consider this to be a command station hookup, here we have a DCC command station. Here's our DC brake signal generator, and over here we have the AB wire coming out, which is DCC. That's actually hot water here, but DCC. Over here we have the CD wire coming out, which is DC when the thing is in the automatic mode, and this is cold water in this case. Now further down we've got our Bitswitch, which is really the faucet for the laundry tub, but this is our Bitswitch picking up one of these two lines, either cold or hot water, or using our analogy DC or DCC current. The Bitswitch takes whichever one is required to the track to do what it's supposed to do, and sends that out to the track brake section, which is this hose. So for this hose, you can have either cold water going out it or hot water going out of it, depending on which pipe the faucet's picking up off of. So again, using our analogy, there's a switch on this DC brake signal generator, recall, and you can throw that switch from automatic to manual. If you throw it to manual, it puts DCC on this line instead of DC. So now operating in the manual mode, now we have DCC on this wire coming out also, or in the case of our laundry tub, let's say we switched it so hot water was coming down this pipe as well as this pipe. So regardless of which way you turn the Bitswitch down here, you'd have hot water coming out the hose to the track section. In this case it would be DCC current coming out to the track section, regardless of which way the DCC-Bitswitch relays were thrown. It would have DCC coming into it on both sets of wires, so it will always put DCC out. This would be manual operating mode, and the position of any of these bit switches on the layout, however many of them there were, one like our test layout, or if you had a layout with 10 or 20, it wouldn't matter what position they were in, because they'd always be getting DCC on both their inputs wires and sending it out to the brake sections. To demonstrate the manual mode, I'm going to manually set the bit switch to red. There's just one train on the track, so that train will come across the test contact right about now, and since the block is red, the bit switch switched from DCC to DC current on the stop section, which brought that engine to a stop. Now that's going to wait there until the bit switch is set back to the green position, which normally would be done by the second train. There's no second train on the track, so that engine's just going to sit there. What I'm going to do to demonstrate manual mode, I'm going to walk over to the DC brake signal generator and switch it from automatic to manual mode, which will put DCC onto the track even though the bit switch is red. And you can see when I switch that DC brake signal generator from the automatic to the manual mode, it switched the output on wires C and D going to the bit switch from DC to DCC current. So regardless of what position the bit switch is in, be it red or be it green, it's always sending DCC to the brake section. What this means is the bit switch is more or less become invisible. It doesn't matter what position they're in. All sections of the track will have DCC current for manual control of them. Said another way, you can run the trains manually with the DC brake generator set to the manual position, and the bit switches won't have any effect. When you're ready to go back to automatic mode, then you just switch the DC brake signal generator back to the automatic position, and the bit switches will become operational again. If you have an NCE DCC system such as I do, one other option you have different than DCC bit switch is hooking up one of these devices called a mini panel. But this has to be used with an NCE system. If you have a brand other than NCE, you can't do this. But if you have NCE, one nice feature of this is you don't have to cut any blocks in the track or anything. Your track can be pretty much continuous. It works well with one loco. However, if you get two locos or more locomotives on the track, it gets cumbersome with this, because every time you send a command, you basically have to tell what engine number you're addressing. If you have different engines, you're trying to handle a lot of different numbers, and it gets pretty complex.